Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Take a moment, if you haven't already, to get truly comfortable. Let your body settle into wherever you are right now. Where in the world are you watching from? A quiet bedroom where the day has finally released its hold? A cozy corner where you've claimed a few moments of peace? Wherever you are, you're welcome here. Tonight we're going to explore one of the most profound questions humanity has ever asked. What came before the Big Bang? It's a question that seems to contradict itself, that pushes against the very limits of language and thought. We'll discover how scientists have approached this seemingly unanswerable riddle, understand the strange physics that might allow us to speak meaningfully about _quote, _0_ when time itself didn't exist, and contemplate what the newest theories and discoveries tell us about the true beginning of everything. It's a journey that spans the entire history of cosmological thought, from ancient creation myths to cutting-edge quantum physics. But don't worry. This isn't going to be an overwhelming cascade of mathematics and jargon that leaves you more confused than when we started. Instead, we'll move slowly and carefully through each idea, taking our time to let complex concepts settle before building on them. By the end, I think you'll find that the question of what came before the Big Bang is less about finding a final answer and more about discovering how the question itself transforms our understanding of existence. If you enjoy these calm explorations of the cosmos and our place within it, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for making this community what it is. So settle in now, let your shoulders drop away from your ears, take a slow breath, deep enough that you feel your ribs expand, and let's begin our slow drift through the biggest question we can ask. There's nowhere you need to be right now, nothing you need to solve or understand completely. Just listen and let the story of the beginning unfold. If you drift away before we reach the end, that's exactly as it should be. What came before the Big Bang? Even asking the question feels strange, doesn't it? We're asking what happened before time began, what existed before existence itself. It's the kind of question that seems to eat its own tail, that dissolves into paradox the moment we examine it closely. And yet, for as long as humans have been capable of wonder, we've been asking exactly this kind of impossible question. The ancient Greeks wrestled with it in their own way. They asked, how can something come from nothing? Their philosophers, sitting in sun-drenched courtyards, debating beneath olive trees, understood that creation posed a fundamental problem. If the universe had a beginning, what caused that beginning, and what caused the cause? The chain of causation seemed to stretch backward infinitely, each answer only spawning a new question. Medieval theologians faced the same puzzle. They solved it, or thought they did, by placing God outside of time entirely. God wasn't the first cause in a chain of causes. God was the uncaused cause, existing in an eternal now that had no before or after. Whether or not you find that solution satisfying, you have to admire the intellectual move. They recognise that to escape the infinite regress, you needed something that didn't play by the same rules as everything else. What's fascinating is that modern cosmology has arrived at a surprisingly similar conclusion, though through entirely different means. When Albert Einstein's equations suggested that the universe might have had a beginning, he initially rejected the idea. It seemed too much like a creation event, too theological. Einstein added a term to his equations, the cosmological constant, specifically to make the universe eternal and unchanging. He wanted a cosmos that had always existed, that didn't require a beginning. But the universe had other plans. In 1929, Edwin Hubble discovered that distant galaxies were rushing away from us. The universe wasn't static at all. It was expanding, and if it was expanding now, that meant it was smaller in the past. Rewind far enough, and you arrive at a moment when everything we can see, all the matter and energy in the observable universe, was compressed into an infinitesimally small point, a beginning, the Big Bang. Einstein eventually called his cosmological constant his greatest blunder, though that's another story for another time. What matters now is that science had arrived at what seemed like a creation event. 13.8 billion years ago, something happened. Time began. Space began. The universe began. But this only makes our question more urgent, more impossible. If time itself began at the Big Bang, how can we meaningfully ask what came before? Before is a time word. It requires time to already exist. St. Augustine understood this problem back in the 4th century. When asked what God was doing before he created the universe, Augustine replied that there was no _quote_1_ time itself was part of creation. Asking what came before time is like asking what's north of the North Pole. The question contains a category error, a misunderstanding of what time actually is. And yet we keep asking. We can't help ourselves. Something in the human mind rebels against the idea of an absolute beginning, a first moment with nothing before it. It feels incomplete, like a story that starts in the middle, and this brings us to something equally remarkable. In the last few decades, scientists have found ways to ask this impossible question that might actually lead somewhere, that might give us a glimpse of what _quote_2_ could mean, even when before doesn't exist. Which leads us naturally to consider how we even discovered that the universe had a beginning in the first place, and why that discovery was so shocking when it arrived. The story of how we discovered the Big Bang is itself a tale of things coming from nothing, of finding something no one was looking for. In 1964, two scientists named Arno Penzias and Robert Wilson were trying to eliminate an annoying hiss from a radio antenna at Bell Labs in New Jersey. They cleaned out the antenna. They removed the pigeons that had been nesting inside and meticulously scrubbed away what they politely called dielectric material, which is to say, pigeon droppings. But the hiss remained. No matter where they pointed their antenna in the sky, no matter what time of day or night, the hiss persisted. It was faint but constant, a gentle whisper of radio noise coming from everywhere at once. What they had stumbled upon, though they didn't know it yet, was the afterglow of creation itself, the cosmic microwave background radiation. The oldest light in the universe, light from the Big Bang, still fills the universe. About 380,000 years after the beginning, the universe had expanded and cooled enough for atoms to form. Before that moment, the cosmos was an opaque fog of particles and light. Everything so hot and dense that photons couldn't travel more than a tiny distance before being absorbed and re-emitted. But when atoms formed, light was suddenly free to travel. The universe became transparent, and that first light set out on a journey that continues to this day. We call it the cosmic microwave background, or CMB. It's not visible to our eyes because the expansion of the universe has stretched those photons, shifting them from visible light down into microwave wavelengths. But it's there, filling every cubic centimetre of space, a faint glow with a temperature of about 2.7 degrees above absolute zero. This is what Penzias and Wilson heard as a hiss. They were listening to the echo of the Big Bang. The discovery won them the Nobel Prize, as well it should have. But what's remarkable about the CMB isn't just that it exists. It's what it tells us. The cosmic microwave background is astonishingly uniform. In every direction we look, the temperature is the same to within a few parts in 100,000. The early universe was extraordinarily smooth, almost perfectly homogeneous. This smoothness poses a problem. One that will lead us toward our answer about what came before. Imagine two regions of space on opposite sides of the observable universe. Both have the same temperature in the CMB. That means they were in thermal equilibrium. They had time to exchange energy and reach the same temperature. But if you calculate how fast information can travel, limited by the speed of light, these regions have never been in contact. They're too far apart. Light from one region hasn't had time to reach the other, not in the entire history of the universe. So how did they know to have the same temperature? How did the universe coordinate itself to be so uniform when the regions we're observing have never been able to communicate? This is called the horizon problem, and for a long time it seemed like a deep mystery, a puzzle that suggested something important was missing from our understanding of the Big Bang. There's another puzzle too, equally strange. The universe appears to be almost perfectly flat. Space doesn't curve in on itself like the surface of a sphere, nor does it curve outward like a saddle. It's flat, or so close to flat that we can't measure any curvature. This requires an extraordinary fine-tuning. Tiny deviations from flatness early in the universe's history would have been amplified as space expanded. For the universe to be as flat as we observe today, the initial conditions had to be set with incredible precision, balanced on a knife's edge. Why would the universe start out that way? What set those initial conditions with such exquisite care? These questions bothered cosmologists deeply. The Big Bang theory explained so much. It explained Hubble's observations of galactic recession. It explained the abundance of light elements like hydrogen and helium that were forged in the first few minutes. It explained the cosmic microwave background. But it didn't explain these initial conditions, it simply assumed them. And this is where we start to glimpse an answer to what came before, because in the early 1980s, a physicist named Alan Guth proposed something radical. What if there was a period before the universe we observe when space expanded far faster than the speed of light? What if, in the tiniest fraction of a second after the beginning, the universe underwent a period of exponential expansion, doubling in size again and again in rapid succession? This idea came to be called inflation. If inflation happened, it would solve both problems at once. All the regions we observe would have started out close together, in contact, able to reach the same temperature. Then inflation stretched space, pulling those regions apart faster than light could travel between them. The universe would naturally be flat because inflation stretched out any curvature, the way inflating a balloon smooths out wrinkles on its surface. Inflation was elegant, almost beautiful in its simplicity. But it also opened a door to an even stranger possibility. If inflation happened, what started it? What came before inflation? And could that same process tell us what came before the Big Bang itself? That question, gentle and persistent, leads us to the realm of quantum mechanics, where the rules of cause and effect start to behave in unexpected ways. There's a concept in quantum physics that feels like it should be impossible, and yet it's been verified in laboratories thousands of times. It's called quantum fluctuation, and it tells us that nothing is never truly nothing. Even in the emptiest vacuum, in the darkest void far from any matter or energy, something is always happening. Picture empty space, or try to. You might imagine perfect stillness, a blank canvas, pure nothingness. But quantum mechanics says this picture is wrong. The vacuum seethes with activity. Particles and their antimatter twins pop into existence, live for the briefest instant, and then annihilate each other, vanishing back into nothing. This isn't speculation or metaphor. These virtual particles, as they're called, have measurable effects. They alter the energy levels of atoms. They create a tiny force between metal plates in an experiment called the Casimir effect. The reason this happens has to do with Heisenberg's uncertainty principle, one of the bedrock ideas of quantum physics. The principle tells us that there are pairs of properties, like position and momentum, or energy and time, that cannot both be known with perfect precision. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of our measuring instruments, it's a fundamental feature of reality. For energy and time, the uncertainty principle says that you can borrow energy from nothing as long as you pay it back quickly enough. The shorter the time interval, the larger the energy you can borrow. Virtual particles are reality taking out a loan and repaying it before the universe notices. They exist in the gap between what we can measure and what is fundamentally determinable. This has profound implications for our question about what came before the Big Bang. If quantum fluctuations can create particles from nothing, could a quantum fluctuation create a universe? Could the entire cosmos be the result of reality borrowing energy from the void and, in some sense, not yet paying it back? The physicist Alexander Vilenkin proposed exactly this in the 1980s. He suggested that the universe could have tunnelled into existence from nothing through a quantum process. In quantum mechanics, particles can do something impossible in classical physics. They can tunnel through barriers, appearing on the other side without having the energy to climb over. An electron in an atom, for instance, has a small but non-zero probability of suddenly being found outside the atom, even though it doesn't have enough energy to escape. Vilenkin applied this idea to the universe itself. Perhaps the universe tunnelled into existence from a quantum void, from a state of absolute nothing. Not empty space, but no space at all. No time, no matter, no energy. Just the mathematical possibility of existence encoded in the laws of quantum mechanics. And then, spontaneously, without cause or trigger, a tiny bubble of space-time appeared. This bubble immediately began inflating, and that inflation became the Big Bang we observe. It's a dizzying idea. It suggests that the universe is, in a very real sense, the ultimate free lunch. The total energy of the universe might be exactly zero. The positive energy in matter and radiation is balanced by the negative energy in gravitational fields. Add them up, and you get nothing. The universe could be a quantum fluctuation that's large enough and stable enough to persist, to inflate, to evolve into galaxies and stars and planets and us. But this raises questions as deep as the ones it answers. If the universe came from nothing, where did the laws of quantum mechanics come from? Where did the possibility of tunnelling, of fluctuation, of existence itself come from? Are the laws of physics eternal, existing in some platonic realm outside of space and time, or did they too somehow emerge from nothing? Some physicists, like Stephen Hawking, suggested that asking what came before the Big Bang might be like asking what's south of the South Pole. There simply is no south of the South Pole. The question is based on a misunderstanding. In Hawking's model, which uses something called imaginary time in its mathematics, the universe doesn't have a boundary or an edge in time. The Big Bang isn't a moment when time began, but rather a point where time becomes like another dimension of space. Time and space merge in such a way that quote 4 loses its meaning. This connects to something I find deeply fascinating about the nature of time itself, and how our ordinary experience of past, present and future might be only part of the story. In Einstein's relativity, time is not separate from space. They form a unified fabric called space-time. Events don't happen in space and then in time. They happen in space-time at specific coordinates that include both where and when. From this perspective, the entire history of the universe, from the Big Bang to the present moment to whatever far future awaits us, exists as a single four-dimensional structure. The flow of time, the sense that the present moment is somehow special, might be an illusion created by our consciousness. The past isn't gone. The future isn't yet to come. They all exist, laid out in the space-time manifold like cities along a highway. If this view is correct, then asking what came before the Big Bang might indeed be meaningless, not because the question is too hard, but because it's based on a misconception about what time is. The universe doesn't exist in time. Time exists in the universe, as one dimension of the space-time structure. There is no quote 5 of the universe, no quote 6 the Big Bang, because those concepts require a time and space that the universe itself provides. And yet, even this elegant resolution leads us to new questions, new mysteries about the fundamental nature of reality, and whether our universe might be just one among many. There's another possibility, one that's become increasingly prominent in theoretical physics over the last few decades. What if our Big Bang wasn't the beginning of everything? What if it was just one beginning among an infinite number of others? This is the idea of eternal inflation, and it transforms our question about what came before into something even stranger and more wonderful. Remember inflation, that brief period of exponential expansion we discussed earlier. In most versions of inflation, it starts everywhere at once and then stops everywhere at once, leaving behind a universe that expands more sedately, cooling and forming atoms and eventually galaxies. But the physicist André Linde realised that inflation might not stop everywhere at the same time. In fact, in most quantum versions of inflation, it can't. Here's how it works. Imagine a field, something like the Higgs field but different, pervading all of space. This field is in a high-energy state, and that high energy drives inflation, causing space to expand exponentially. Quantum fluctuations make the field's energy vary slightly from place to place. In some regions, the fluctuations push the field down toward a lower energy state, and inflation stops there. Those regions become universes like ours, pockets of normal space-time where the ordinary Big Bang expansion takes over. But here's the crucial part. While inflation is stopping in some regions, it continues in others. And because inflation creates new space so rapidly, the volume of space that's still inflating actually grows faster than new pockets of normal space-time are forming. Inflation never ends globally. It only ends locally in finite patches that become individual universes. This means inflation is eternal into the future. Once it starts, it can't completely stop. New universes are constantly budding off from the inflating space, like bubbles forming in an infinite sea of foam. Each bubble is a universe unto itself, with its own Big Bang, its own history, its own galaxies and stars. We live in one such bubble. Our Big Bang was the moment when inflation stopped in our patch of the larger inflating space. If this is true, then what came before our Big Bang was inflation, a period of exponential expansion that's still happening elsewhere, outside our bubble universe, creating new universes even now. But this only pushes the question back one step. What started inflation in the first place? Did it have a beginning? Or has it been happening eternally into the past as well? Vilenkin and his colleagues have proven mathematical theorems suggesting that even eternal inflation must have had a beginning. Any universe that's expanding on average, when you look at it over long enough timescales, cannot be eternal into the past. There must be a boundary, a beginning to the inflating region. So we're back to our original question, just in a different form. What came before inflation began? One possibility, strange but increasingly respectable, is that our universe budded off from a previous universe. Not through inflation, but through a black hole. We know that black holes create singularities, points where the curvature of space-time becomes infinite, and our equations break down. We can't describe what happens at a singularity using general relativity. The math simply stops working. But some physicists have suggested that on the other side of a black hole singularity, space-time might re-expand, creating a new universe. From the outside, it looks like a black hole, a region of extreme gravity from which nothing can escape. But from the inside, it looks like a Big Bang, an expanding universe. Every black hole in our universe might contain a baby universe, and our universe might itself be inside a black hole in some parent universe. This idea, sometimes called cosmological natural selection, was proposed by Lee Smolin. If it's correct, then universes reproduce. Each universe creates black holes, and those black holes spawn new universes. Over time, you'd expect universes to evolve to be good at making black holes, the way organisms evolve to be good at surviving and reproducing. The laws of physics themselves might be subject to a kind of natural selection, with successful universes, those that make many black holes, passing on their physical laws to their offspring. It's a beautiful idea, though it's extremely difficult to test. We can't see inside black holes. We can't observe these baby universes. But it suggests an answer to what came before our Big Bang. Another universe, and before that, another, in an infinite chain of cosmic reproduction stretching back forever. Or perhaps not forever. Perhaps the chain has a beginning somewhere, a first universe that emerged from nothing through the quantum processes Vilenkin described. Or perhaps time itself is cyclical. and the chain of universes loops back on itself, so that the first universe in the sequence is also the last, and before and after lose their meaning entirely. These ideas take us to the very edge of what we can meaningfully discuss with science. We're approaching territories where physics and philosophy and even theology begin to blend together, where the questions we can ask exceed the questions we can answer, at least for now. But there's something profound about reaching this edge, about pushing human thought to its absolute limits and discovering both what we know and what we might never know. Which brings us to a different kind of question, one about the nature of time itself, and whether the distinction between past and future might be less fundamental than it seems. We experience time as a river, flowing in one direction, carrying us from past through present toward future. Memories exist only of what has been, never of what will be. We can influence the future, but the past is fixed, immutable, beyond our reach. This seems so obvious, so fundamental to our experience, that it's hard to imagine time could be any other way. And yet, when you look closely at the laws of physics, the flow of time becomes deeply mysterious. At the most fundamental level, the equations that govern the universe don't distinguish between past and future. If you filmed a planet orbiting a star and played the video backward, you'd see something that obeys Newton's laws of motion just as well as the forward version. Microscopically, at the level of individual particles and forces, physical laws are time-symmetric. They work the same way forward and backward. The same is true in quantum mechanics and even in Einstein's general relativity. The equations don't have a built-in arrow of time. They don't care whether time is running forward or backward. If someone showed you the equations describing a particle's motion, without telling you which direction time was flowing, you couldn't tell. So where does the arrow of time come from? Why do we experience time flowing in one direction when the fundamental laws are indifferent? The answer seems to lie in something called entropy, a concept from thermodynamics. Entropy is often described as disorder, though that's not quite right. It's more accurately a measure of the number of ways a system can be arranged microscopically, while looking the same macroscopically. A broken egg has higher entropy than an intact egg because there are many more ways to arrange the molecules into a broken, scrambled mess than into a perfectly formed egg. The second law of thermodynamics says that entropy always increases in a closed system. Eggs break, they don't unbreak. Coffee cools, it doesn't spontaneously heat up. The universe tends toward disorder. But this only pushes the mystery back a step. Why was entropy low in the early universe? The Big Bang started in an extraordinarily low entropy state, everything compressed into a tiny, hot, dense, but remarkably uniform and organised condition. Since then, entropy has been increasing. And that increase defines the arrow of time. The past is the direction of lower entropy. The future is the direction of higher entropy. If the universe began in a high entropy state, there would be no arrow of time. No eggs would break because eggs couldn't form in the first place. No coffee would cool because there would be no temperature differences. The universe would be a featureless equilibrium soup, and nothing interesting would ever happen. But our universe didn't start that way. It started in a very special, very low entropy state, and we don't fully understand why. This low entropy beginning is, in a sense, the ultimate boundary condition of our universe. It's baked into the initial conditions of the Big Bang. But where did those initial conditions come from? Why did the universe start with such low entropy when the vast majority of possible initial states would have much higher entropy? Sean Carroll, a physicist who has thought deeply about these questions, suggests that our universe might be a small, low entropy fluctuation in a much larger, eternally existing multiverse. Most of the multiverse is in thermal equilibrium, a state of maximum entropy where nothing changes and no times arrow exists. But occasionally, through random quantum fluctuations, a region of lower entropy forms. Most such fluctuations are small and brief, but very rarely a fluctuation large enough and ordered enough to contain a Big Bang appears. We find ourselves in such a fluctuation, not by design, but because only in these rare low-entropy regions can structures like stars and planets, and eventually life arise. It's an application of... Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. It's an application of the anthropic principle. We observe a universe with an arrow of time because we couldn't exist in a universe without one. But even this explanation requires something eternal, something that exists before our Big Bang in some meaningful sense. It requires a larger multiverse with its own laws and structure. And so we're back to the same question in yet another form. What is the ultimate foundation? What exists without needing something before it? There's a philosopher's answer that deserves mention here. Gottfried Leibniz, back in the 17th century, asked why there is something rather than nothing. He argued that there must be a sufficient reason for everything that exists, and ultimately, that chain of reasons must terminate in something whose reason for existing is contained within itself. Something that exists by necessity rather than contingency. Modern physics has taken this ancient question and given it new form. The laws of quantum mechanics allow, perhaps even require, that things can come from nothing. The structure of space-time, the nature of inflation, the existence of a multiverse. All these might flow necessarily from the mathematics of quantum field theory and general relativity. Perhaps asking what came before the Big Bang is like asking why 2 + 2 = 4. Is not that something made it that way, is that it couldn't be any other way. Or perhaps, as some physicists and philosophers suggest, existence itself is the most fundamental fact requiring no explanation. The universe exists because non-existence is incoherent, because nothing is inherently unstable and collapses into something. This is a deep idea, one that transforms our question from what came before to why is there a before at all? And with that thought settling gently, we find ourselves ready to explore what modern observations and experiments are telling us about these ancient questions. The cosmic microwave background isn't just a uniform glow filling the universe. When you look closely, when you map it with exquisite precision, you find patterns, tiny temperature variations, just a few parts in 100,000, rippling across the sky. These patterns are the seeds of everything that came after. The galaxies, the stars, planets, us. We all grew from these primordial fluctuations. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, mapped these temperature variations with unprecedented detail. Later, the Planck satellite improved on that precision. What they revealed was extraordinary. The patterns in the CMB match with remarkable accuracy the predictions of inflation. They show exactly the kind of quantum fluctuations you'd expect if the universe underwent exponential expansion in its first fraction of a second. Here's what makes this so compelling. During inflation, quantum fluctuations in the inflaton field, the field driving inflation itself, got stretched to enormous sizes. These fluctuations created slightly denser and slightly less dense regions in the early universe. After inflation ended and the Big Bang era proper began, these density variations evolved under gravity. Denser regions pulled in more matter, becoming denser still, eventually forming galaxies. Less dense regions became the voids between galaxies. But before any of that structure formed, when the universe was still an opaque fog of particles and light, these density variations left an imprint on the cosmic microwave background. Slightly denser regions had slightly higher pressure, which created sound waves. Ripples moving through the primordial plasma at a significant fraction of the speed of light. when the universe became transparent and light was free to travel, it carried with it a snapshot of these sound waves frozen in place. This is what we see in the CMB. The pattern of hot and cold spots is literally the pattern of sound waves in the plasma that filled the universe when it was just 380,000 years old. Cosmologists call these patterns acoustic oscillations. They're the echoes of vibrations in the newborn universe, and they tell us an enormous amount about what the universe was like at that time. The size of the largest hotspots, for instance, tells us how far sound could travel in 380,000 years. This depends on the speed of sound in the primordial plasma, which in turn depends on the density and composition of matter and energy. By measuring the pattern of spots, we can determine what the universe was made of, how much ordinary matter, how much dark matter, how much dark energy. It's like cosmic archaeology, reading the composition of the early universe from the patterns imprinted on ancient light. And what we find matches inflation's predictions beautifully. The fluctuations are almost perfectly scale invariant, meaning they have the same amplitude on all size scales. This is exactly what you'd expect from quantum fluctuations stretched by exponential expansion. If some other process created these fluctuations, it would be an astonishing coincidence that they happen to look exactly like what inflation predicts. There's another signature we're searching for, one that would be even more direct evidence of inflation. Gravitational waves. Not the kind we detect from colliding black holes, but primordial gravitational waves. Ripples in space-time itself created during inflation. These waves would have left a distinctive pattern in the polarization of the cosmic microwave background, a swirling pattern called B-modes. In 2014, a team using the BICEP 2 telescope in Antarctica announced they had detected these B-modes. The news was greeted with tremendous excitement. If confirmed, it would be direct evidence of inflation, proof that the universe underwent exponential expansion in its earliest moments. But further analysis revealed that the signal was likely caused by dust in our own galaxy, not primordial gravitational waves. The search continues. If we do detect primordial B-modes, it will tell us the energy scale at which inflation occurred. This, in turn, constrain theories about what came before, about what caused inflation to start and what the universe was like in that first, unimaginably brief instant. It might give us a window into physics at energies far beyond what we can reach in any particle accelerator, energies where the forces of nature unify, where quantum mechanics and gravity meet. Even without B-modes, though, the patterns in the CMB are telling us something profound. They're telling us that the universe we observe today, in all its vast complexity, grew from quantum fluctuations, from the inherent uncertainty and randomness at the heart of quantum mechanics. Every galaxy exists because of a quantum fluctuation amplified by inflation to cosmic scales. We are, quite literally, children of quantum uncertainty. This connects back to our question about what came before. If quantum fluctuations can create galaxies, can they create universes? The same mathematics that predicts the patterns we see in the CMB also allows, in principle, for the entire universe to be a quantum fluctuation, a bubble of space-time tunneling into existence from nothing. The evidence from the CMB doesn't prove this happened, but it shows that quantum processes can have macroscopic, even cosmic consequences, which leads us to consider what other evidence might guide our thinking about the universe's origin, and whether there are ways to test these ideas beyond the cosmic microwave background. One of the strangest discoveries in all of cosmology came from measuring the universe's expansion rate at different times in its history. Scientists expected to find that gravity was slowing the expansion down. After all the matter in the universe pulls on all the other matter. The expansion should be decelerating, slowing over time like a ball thrown into the air, gradually losing speed as gravity pulls it back down. But in 1998, two teams of astronomers announced something shocking. The expansion isn't slowing down. It's speeding up. The universe is accelerating, expanding faster and faster as time goes on. This discovery won the Nobel Prize and revolutionized cosmology. It meant that something is pushing space apart, some form of energy that fills the universe and drives this acceleration. We call it dark energy, though the name tells us almost nothing about what it actually is. The simplest explanation is that it's the energy of empty space itself, the vacuum energy we discussed earlier. Remember those quantum fluctuations, virtual particles popping in and out of existence? Each fluctuation carries energy, and when you add up all the fluctuations across all of space, you get a constant energy density associated with the vacuum. This vacuum energy has a strange property. Unlike matter, which dilutes as the universe expands, vacuum energy stays constant. If you double the volume of a box, the amount of matter inside stays the same, so the density drops by half. But the amount of vacuum energy doubles, keeping the density constant. This constant energy density creates a kind of anti-gravity, pushing space apart rather than pulling it together. Einstein's equations allow for exactly this kind of energy through the cosmological constant, that same term Einstein added and later removed from his equations. It turns out the universe needs a cosmological constant after all. The value we observe is small but not zero, and it's causing the universe to expand exponentially, though much more slowly than during inflation. Here's where it connects to what came before the Big Bang. If vacuum energy is real, if empty space has energy, then inflation might be the result of a different kind of vacuum energy, one much, much larger than what we observe today. In the very early universe, space might have been in a high-energy vacuum state, and that enormous vacuum energy drove inflation. Eventually, the universe transitioned to a lower-energy vacuum state, the one we observe today, and inflation ended. But if this is correct, it raises profound questions. Why did the universe start in a high-energy vacuum state? Why didn't it start in the low-energy state we observe now? Or in the true ground state with zero vacuum energy? The answer might be that our universe is one bubble in an eternally inflating multiverse, and different bubbles settle into different vacuum states with different amounts of vacuum energy. In some bubbles, the vacuum energy might be so large that inflation never stops. In others, it might be negative, causing the universe to collapse almost immediately after forming. Only in bubbles where the vacuum energy happens to be small and positive, or where it's zero or slightly negative but the universe is large enough to survive for billions of years, only in those bubbles can galaxies and stars and life arise. This is another application of the anthropic principle. We observe a universe with a small, positive cosmological constant, not because that's the only possibility, but because we couldn't exist in most other types of universes. Our existence selects for the kind of universe we observe. It's a controversial idea. Some scientists find it deeply unsatisfying, a retreat from explanation into mere observation of the fact that we exist. Others see it as a legitimate part of scientific reasoning, especially in a multiverse where different regions have different physical properties. What's remarkable is that we can measure the vacuum energy. It's not just theoretical speculation. We observe its effects in the accelerating expansion of the universe. The Hubble Space Telescope and later observations from ground-based telescopes measured distant supernovae and used them as standard candles to determine distances. What they found was that distant supernovae, which exploded billions of years ago, are farther away than they should be if the universe's expansion had been constant or decelerating. This means space itself has stretched more than we expected, which means the expansion rate has increased. The evidence is robust and has been confirmed through multiple independent methods. Dark energy is real. The vacuum has weight, though it's a strange kind of weight that pushes rather than pulls. And if the vacuum has energy now, it's not unreasonable to think it might have had different energy at different times in the universe's history. The vacuum might not be stable. It might be able to transition from one energy state to another, like water transitioning from liquid to ice. Inflation could be the result of such a transition, a phase change in the fabric of space itself. This brings us to a fascinating and somewhat unsettling possibility. If the vacuum can transition from one state to another, what if it transitions again in the future? What if the vacuum we live in now isn't stable but metastable, existing in a local minimum of energy rather than the true ground state? Quantum mechanics says that even if we're in a local minimum, there's a probability, however small, of tunneling to a lower energy state. If this happens, a bubble of lower energy vacuum would form somewhere in the universe and expand at the speed of light. Everything it touches would be destroyed, not in the sense of matter being obliterated, but in the sense of the fundamental properties of space changing. The laws of physics inside the bubble would be different. Atoms might not be able to form. The constants of nature that make chemistry and biology possible would have different values. But this is a worry for the far future, if it's a worry at all. The probability of such a vacuum decay happening in any given region, in any given billion years, is extraordinarily small. The universe is far more likely to end through the heat death, the gradual dilution of all energy as expansion continues, than through vacuum decay. What matters for our question about what came before is that vacuum energy and transitions in vacuum energy might be the key to understanding the beginning. Our Big Bang might have been such a transition, a bubble of lower energy vacuum forming in a sea of higher energy inflating space. And this brings us to the idea that the Big Bang might not have been the only one, and that time itself might extend far beyond what we can observe. There's a fundamental limit to what we can observe. It's not a limit imposed by our telescopes or our theories. It's a limit imposed by the speed of light and the age of the universe. We call it the cosmic horizon, and it separates the observable universe from the unobservable. Light travels fast, but not infinitely fast. It takes time for light to cross space. Light from the sun takes about 8 minutes to reach Earth. Light from the nearest star beyond the sun, Proxima Centauri, takes a bit over 4 years. Light from distant galaxies has been travelling toward us for billions of years. The most distant light we can see, the cosmic microwave background, has been travelling for 13.8 billion years, nearly the entire age of the universe. But here's the subtlety. The observable universe isn't 13.8 billion light-years in radius. It's much larger, about 46 billion light-years. The reason is that space has been expanding while the light was travelling toward us. The galaxies that emitted the CMB photons we see today were much closer to us when they emitted that light. Since then, they've been carried away by the expansion of space, and they're now far beyond the naive light travel time distance. Beyond this horizon, there are regions of space we can never observe, not because they don't exist, but because light from them hasn't had time to reach us yet. As time goes on, our horizon expands. We can see farther into the universe, more galaxies come into view. But because the expansion is accelerating, there are galaxies that are receding from us faster than light can catch up. We will never see them, no matter how long we wait. This horizon is crucial for understanding what came before the Big Bang, because it tells us that our observations are fundamentally limited. We can only see a finite portion of space. Beyond that portion, the universe might be completely different, or it might be the same, extending infinitely. We can't know through observation alone. If eternal inflation is correct, then beyond our horizon, there's more inflating space and other bubble universes. Each bubble is like an island universe, causally disconnected from the others. Information cannot pass between them. They might as well be separate universes entirely. Our Big Bang was the formation of our bubble, but other bubbles formed before ours and are forming even now, scattered throughout the inflating space like soap bubbles in an infinite foam. This raises a question about the meaning of before. If inflation is eternal into the future, if new bubbles are constantly forming, then in some sense Big Bangs are happening all the time, just not in our region of space. From the perspective of the inflating space, there is no single moment of creation, no beginning. There's an eternal process of bubble formation, each bubble experiencing its own local beginning, its own Big Bang. But Vilenkin's theorem suggests that inflation itself must have had a beginning. You can't have eternal inflation into the past. At some point, there must have been a first moment, a boundary beyond which time doesn't extend. This boundary might be a quantum creation event, the entire inflating space tunneling into existence from nothing. Or it might be something else, a singularity where our physics breaks down and we can't say what happened, because the mathematics no longer works. Stephen Hawking suggested a way around this hard boundary. In his no-boundary proposal, worked out with James Hartle, the universe doesn't have an edge in time. Instead, as you go back toward the Big Bang, time gradually becomes more like space. The distinction between time and space blurs and eventually disappears. The question, what came before, becomes like asking what's north of the North Pole. The question assumes a direction, a before that simply doesn't exist. In this model, the universe is finite in time but has no boundary. It's like the surface of a sphere, which is finite but has no edge. You can travel forever on the surface of a sphere and never fall off, never reach a boundary. Similarly, in Hawking's universe, you can go back in time as far as you like, but you never reach a moment where time began because time gradually transforms into space. This is mathematically elegant, but it's hard to visualize and even harder to test. We can't observe the moment of the Big Bang directly. We can only see its aftermath. The patterns in the CMB, the abundance of elements, the large-scale structure of galaxies, all these give us clues about the very early universe. But they don't tell us definitively what happened at the first instant or whether there even was a first instant. What we can say is that the universe we observe is consistent with having emerged from a hot dense state 13.8 billion years ago. Everything we see points back to that moment, and the question of what came before, or whether before is even meaningful, remains at the boundary of what science can currently address. But that boundary is not fixed. It's moving. New theories, new observations, new ways of thinking about time and space might push that boundary farther back. We might find ways to test the multiverse hypothesis, or to detect signatures of pre-Big Bang physics in the cosmic microwave background. We might develop a theory of quantum gravity that tells us what happens at singularities, that extends our understanding beyond the point where current theories break down. And this brings us to one of the most ambitious attempts to answer what came before, the idea that the universe might be cyclical, endlessly repeating in an infinite series of big bangs and big crunches. Human cultures across the world have imagined time as cyclical. The seasons repeat, day follows, night follows day, generations rise and fall. Ancient Hindu cosmology speaks of cycles of creation and destruction spanning billions of years. The Mayans had their long count calendar, marking vast cycles of time. The Stoics in ancient Greece believed the universe was periodically consumed by fire and reborn, eternally repeating the same history in exact detail. Modern cosmology has flirted with similar ideas, though in more rigorous mathematical form. The cyclic universe is a model in which the Big Bang is not the beginning of everything, but just the latest in an infinite series of cosmic rebirths. The universe expands from a Big Bang, evolves, and eventually contracts in a big crunch. At the moment of maximum compression, something happens, a bounce, and the universe expands again in a new Big Bang. This cycle repeats infinitely. The appeal of cyclic models is obvious. They avoid the problem of the first cause. There is no beginning because the cycles have always been happening and will always continue. They solve the low entropy problem by suggesting that each cycle somehow resets the entropy, allowing for a new period of increasing disorder. And they give a kind of meaning to the universe, a purpose, to endlessly create and recreate itself. But cyclic models face serious challenges. The main one is entropy. The second law of thermodynamics says entropy always increases. In a closed system, disorder always grows. If the universe went through cycles, you'd expect entropy to accumulate from cycle to cycle. Each new cycle would start with higher entropy than the last, and eventually the universe would reach maximum entropy and stop cycling. There would be a final cycle, and that's not truly cyclic. There's also the issue of what happens at the bounce. When the universe contracts down to a point, you get a singularity, a point of infinite density and curvature. General relativity breaks down at singularities. We can't describe what happens there. For a bounce to occur, something needs to prevent the singularity from forming, or something needs to happen at the singularity that we don't yet understand. This requires new physics beyond general relativity. Some modern cyclic models try to address these problems. The ekpyrotic scenario proposed by Paul Steinhardt and Neil Turok suggests that the Big Bang was the result of two brains, higher dimensional objects in string theory, colliding. Before the collision, there was a previous universe, contracting slowly. The collision created an enormous release of energy, which we perceive as the Big Bang. After the collision, the brains bounce apart and the cycle can potentially repeat. In this model, entropy isn't a problem because the collision is violent enough to reset the universe's state. The brains start far apart, slowly approach each other, collide, bounce, and separate again. Each cycle creates a fresh universe with low entropy. The model even makes testable predictions about the pattern of fluctuations in the cosmic microwave background, predictions that differ slightly from standard inflation. So far, the observations favour inflation, but the ekpyrotic scenario hasn't been ruled out. Another approach is loop quantum cosmology, which applies ideas from loop quantum gravity to the very early universe. In this framework, the Big Bang isn't a singularity but a bounce. Quantum effects become important when the universe is very small, and these effects prevent the density from becoming infinite. The universe contracts down to a minimum size, and then quantum gravity creates a repulsive force that causes it to expand again. Loop quantum cosmology suggests that before our Big Bang there was a contracting universe, and that universe is still there, in a sense, on the other side of the bounce. If you could travel back through the Big Bang, you'd emerge into the previous universe. Time extends infinitely into the past, with bounce after bounce, universe after universe. These models are fascinating, but they're still speculative. We don't have a complete theory of quantum gravity yet. Loop quantum gravity is one candidate, string theory is another, and there are others as well. Each makes different predictions about what happens at very high energies and very small scales. Until we can test these predictions, we can't be sure which, if any, is correct. What's important to recognise is that all these models, whether cyclic or not, are trying to address the same deep problem: how to make sense of the Big Bang as a physical event rather than a metaphysical boundary. They're trying to extend physics beyond the point where our current theories break down. They're asking whether we can describe the origin of the universe in purely physical terms without invoking anything outside of the natural world, and they're making progress. We may not have the final answer yet, but we have multiple plausible frameworks, each mathematically coherent, each making predictions that could, in principle, be tested. The question of what came before the Big Bang is becoming a scientific question, not just a philosophical one. We're finding ways to turn the impossible question into something we can study, measure, and eventually perhaps answer. Which brings us to consider the role of quantum gravity more directly and what it might tell us about the very first moment. There are two great pillars of modern physics: quantum mechanics and general relativity. Quantum mechanics describes the world of the very small. The behaviour of particles and fields at atomic and subatomic scales. General relativity describes gravity, the curvature of space-time, the motion of planets and stars and galaxies. Each theory is astonishingly successful in its domain, and they seem to fundamentally contradict each other. The contradiction emerges when you try to apply both at once, when you consider situations where something is both very small and very massive. where quantum effects and gravitational effects are both important. This happens in two places: inside black holes, at the singularity where matter is crushed to infinite density, and at the Big Bang, when the entire universe was compressed into a quantum-scale region. At these extremes, general relativity predicts singularities, points where the curvature of space-time becomes infinite and the theory breaks down. The equations give nonsensical answers like infinities and undefined quantities, but quantum mechanics suggests that singularities shouldn't exist. The uncertainty principle prevents any quantity from being measured with infinite precision, which seems to imply that densities can't actually become infinite. For decades, physicists have sought a theory of quantum gravity, a framework that would unify quantum mechanics and general relativity, that would tell us what happens at singularities. String theory is one of the leading candidates. It proposes that the fundamental constituents of reality are not point particles but tiny, vibrating strings. These strings can vibrate in different modes, and each mode corresponds to a different particle. An electron is one vibration pattern, a quark is another, a photon is yet another. String theory naturally includes gravity. One of the vibration modes of the string corresponds to the graviton, the hypothetical particle that carries the gravitational force. This is remarkable because quantum field theory, the framework underlying particle physics, has trouble incorporating gravity. But in string theory, gravity emerges naturally from the mathematics. The problem is that string theory requires extra dimensions, not just the 3 dimensions of space and 1 of time that we experience, but 10 or 11 dimensions total. The extra dimensions have to be curled up so small that we can't detect them directly. This makes the theory extremely difficult to test. We can't build experiments that probe distances small enough to see the extra dimensions or the strings themselves. Nevertheless, string theory has given us insights into black holes and the early universe. It suggests that singularities are replaced by something smoother, that the infinite densities predicted by general relativity don't actually occur. At the centre of a black hole, instead of a point of infinite density, there might be a small but finite region governed by quantum gravity. Similarly, at the Big Bang, instead of a singularity, there might be a quantum state that we could describe mathematically if we had the full theory worked out. Another approach to quantum gravity is loop quantum gravity. Instead of starting with strings in a background spacetime, loop quantum gravity starts with spacetime itself and quantizes it. Space is not continuous but discrete, made of finite indivisible quanta of volume. Time is similarly discrete. There is a smallest possible unit of volume and a smallest possible interval of time set by the Planck length and Planck time. At these scales, about 10 to the negative 33 centimetres and 10 to the negative 43 seconds, space and time themselves become granular. It's like zooming in on a photograph until you see individual pixels. The smooth continuum of space-time is an approximation that emerges when you zoom out, when you look at scales much larger than the Planck scale. Loop quantum gravity suggests that the Big Bang singularity is replaced by a bounce. As the universe contracts, quantum effects become important when the density reaches the Planck density, about 10 to the 93 grams per cubic centimetre. At that point, quantum repulsion dominates over gravitational attraction, and the universe bounces, expanding again. Before the Big Bang, there was a contracting universe, and the Big Bang was the moment of maximum compression and subsequent bounce. Both string theory and loop quantum gravity are incomplete. Neither has been experimentally confirmed, but they give us frameworks for thinking about quantum gravity, for extending physics into regimes where both quantum mechanics and general relativity are important, and they suggest that the Big Bang might not be the absolute beginning, the impassable barrier that it appears to be in classical general relativity. There's another intriguing possibility, one that emerges from thinking about the holographic principle. This principle, inspired by black hole physics, suggests that all the information contained in a volume of space can be encoded on the boundary of that volume, like a hologram. A three-dimensional image is encoded on a two-dimensional surface. If the holographic principle applies to the entire universe, then maybe what we perceive as the Big Bang, the evolution of the universe in time, is actually a kind of projection from a timeless boundary. In this view, the fundamental reality is the boundary, and time is emergent, arising from the relationships encoded on that boundary. The question, what came before the Big Bang, would be as meaningless as asking what's outside the universe, because time itself is part of the projection, not part of the fundamental description. These ideas are speculative, at the very edge of current understanding, but they show that physicists are not giving up on the question of what came before. They're developing new tools, new mathematics, new ways of thinking about space and time and causality. The question that seemed impossible, that seemed to contradict itself, is slowly yielding to patient, rigorous thought and the demand that our theories make sense all the way back to the beginning. And as we move into the second half of our journey, we'll explore what these ideas mean for our understanding of existence itself, and whether the universe might be far stranger and more wonderful than we ever imagined. If eternal inflation is real, if our universe is one bubble in an infinite foam of universes, then the multiverse is not just a possibility but an inevitability. Each bubble is a universe unto itself, with its own Big Bang, its own laws of physics potentially, its own history. We live in one such bubble, and there are countless others, forever beyond our reach. This idea challenges our intuitions about what it means for something to exist. We're used to thinking that existence means observable, measurable, part of the world we can interact with. But the other bubble universes in the multiverse are fundamentally unobservable. No light from them can reach us. No particle, no force, no information of any kind can cross the boundary between bubbles, because that boundary is inflating space, expanding faster than light can travel across it. So in what sense do these other universes exist? They exist in the same sense that distant regions of our own universe beyond our cosmic horizon exist. We can't observe those regions either, but we believe they're there because we have no reason to think the universe stops at the edge of what we can see. The multiverse is just an extension of this reasoning. If inflation is real, and if inflation is eternal, then the multiverse follows as a logical consequence. But the multiverse raises uncomfortable questions for physics. Science is based on testing predictions against observations. If something is unobservable in principle, can we meaningfully say it's part of science? Some physicists argue that the multiverse is metaphysics, not physics, interesting perhaps, but not empirical. Others argue that the multiverse is a prediction of inflation, and since we have evidence for inflation, we should take the multiverse seriously. There's also the question of what varies from universe to universe. In the simplest versions of the multiverse, each bubble has the same laws of physics, but different initial conditions. The constants of nature, like the strength of gravity or the mass of the electron, are the same everywhere. Only things like the amount of matter, the distribution of galaxies, the outcomes of quantum events vary. But in more speculative versions, the laws themselves might vary. String theory, for instance, has a vast landscape of possible vacuum states, perhaps 10 to the 500 or more. Each vacuum state corresponds to different values of the constants of nature, different particles, different forces. If eternal inflation is happening in this string theory landscape, then different bubble universes might settle into different vacua with different physical laws. In some bubbles, gravity might be much stronger than in ours, and stars would burn out in millions of years instead of billions. In others, the electromagnetic force might be weaker, and atoms couldn't hold together. In yet others, there might be extra forces or particles that don't exist in our universe. The multiverse would be astonishingly diverse, a cosmic laboratory exploring every possible variation of the laws of nature. This connects to the anthropic principle we discussed earlier. If the multiverse contains every possible universe, then it's not surprising that we find ourselves in one where the laws happen to allow for stars, planets, and life. We couldn't exist in the vast majority of other bubbles. Our existence selects for a tiny special subset of the multiverse where conditions are just right. Some scientists find this deeply unsatisfying. It seems to give up on the dream of explaining why the laws of nature are what they are. Instead of deriving the constants from some deeper principle, we're just observing that we happen to live in a universe where they have values compatible with life. But others argue that this is simply the correct answer. The constants aren't special. They're randomly selected from a vast distribution of possibilities, and we observe the values we do because we couldn't observe any other. There's a philosophical question lurking here about the nature of explanation. When we ask, quote 18, what kind of answer would satisfy us? Do we want a mathematical derivation showing that the laws couldn't be any other way? Or is it enough to say that all possible laws are realised somewhere in the multiverse, and we're in this particular universe for anthropic reasons? Different scientists have different views. But what's clear is that the multiverse, if real, fundamentally changes how we think about our place in reality. We're not just in one galaxy among billions in the universe. We're in one universe among an infinity of others. The Copernican revolution, which removed Earth from the centre of the cosmos, continues. We're not central in location, not central in time, and if the multiverse is real, not even central in the space of all possible universes. And yet, there's something profound about the fact that we exist at all, that the universe we inhabit allows for complexity and structure and consciousness. Even in a multiverse of infinite possibilities, the particular combination of circumstances that led to you reading these words right now is extraordinary and precious. Which brings us to a question about consciousness itself, and whether the mystery of awareness is connected to the mystery of existence. There's a strange loop at the heart of our investigation. We're conscious beings trying to understand the origin of the universe that gave rise to consciousness. We're made of matter trying to figure out where matter came from. We're part of the universe asking where the universe came from. In a very real sense, the universe is using us to understand itself. Some physicists and philosophers have suggested that consciousness might not be merely an accidental byproduct of cosmic evolution, but somehow fundamental to reality itself. This isn't mysticism or wish fulfillment. It's a response to deep puzzles in quantum mechanics about the role of observation and measurement. Quantum mechanics tells us that before a measurement is made, a particle doesn't have a definite position or momentum. It exists in a superposition, in multiple states at once. Only when we measure it does the wave function collapse, and the particle takes on a definite value. But what counts as a measurement? What causes the collapse? In the Copenhagen interpretation, measurement is fundamental but undefined. It's the point where the quantum world meets the classical world, where probabilities become actualities. But this leaves a mystery. What exactly distinguishes a measurement from any other interaction? Is it the involvement of a conscious observer? Some physicists, most famously Eugene Wigner, suggested that consciousness causes wave function collapse. Only when a conscious being observes the system does it take on definite properties. This would make consciousness a fundamental part of the physics, not an emergent phenomenon, but a basic feature of reality that quantum mechanics requires. Most physicists today don't accept this interpretation. Alternative interpretations of quantum mechanics, like the many worlds interpretation or decoherence theory, avoid giving consciousness a special role. But the questions Wigner raised haven't gone away entirely. The hard problem of consciousness, the question of why subjective experience exists at all, remains one of the deepest unsolved problems in science. There's a connection here to our question about what came before the Big Bang. If consciousness is somehow fundamental, if it's woven into the fabric of reality, then the emergence of conscious beings in the universe might not be an accident but an inevitability, perhaps even the purpose. The universe creates the conditions for consciousness because consciousness is what the universe is fundamentally about. This line of thinking leads to ideas like the participatory anthropic principle, proposed by John Wheeler. Wheeler suggested that observers are necessary to bring the universe into being. In quantum mechanics, the act of observation affects what is observed. Wheeler extended this to the entire cosmos. Perhaps the universe exists because we observe it, because consciousness is there to collapse the cosmic wave function and make reality definite. It's a dizzying idea, one that seems to put the cart before the horse. How can we bring the universe into being when we're products of the universe? Wheeler's answer involved time loops and quantum mechanics. The universe creates us, we observe the universe, and that observation reaches back in time to participate in the creation of the universe. It's a closed loop, with no clear beginning, no clear answer to which came first. Most physicists find this too speculative, too far from what we can test or verify. But it points to something important about the limits of our understanding. We're inside the system we're trying to understand. We can't step outside the universe to see it objectively. Our observations, our theories, our very existence are all part of what we're studying. This doesn't mean we can't make progress. Science has been extraordinarily successful at revealing the universe's workings despite these limitations, but it does suggest humility, a recognition that there might be aspects of reality that are inaccessible to us, not because we lack the right instruments or theories, but because of our position within reality itself. There's another connection between consciousness and cosmology worth considering. Both involve the emergence of something apparently immaterial from something material. The universe emerged from physical processes at the Big Bang. Consciousness emerged from neural processes in brains. In both cases, we're trying to understand how something that seems to require special explanation actually arises from ordinary physics. For consciousness, we have neural correlates, brain states that correspond to particular experiences. We can map which neurons fire when you see red or feel pain. But this doesn't explain why those neural firings are accompanied by subjective experience. Why is there something it's like to be you? Why doesn't the processing happen in the dark without any inner experience at all? Similarly, for the universe, we have mathematical descriptions of the Big Bang, equations that describe the expansion and cooling and formation of structure. But this doesn't explain why there's something rather than nothing. Why does the universe exist at all? Why isn't there just the mathematics, the abstract possibilities, without any physical realization? These might be different versions of the same question. Both are asking about the relationship between the abstract and the concrete, between possibility and actuality, between description and reality. And both might not have answers in the traditional sense of derivations from more fundamental principles. They might be bedrock facts, brute facts, things that are true without having deeper explanations. Or perhaps we're missing something, some deeper level of description that would make both consciousness and existence make sense in a new way. Physics has surprised us before by finding unity in apparently disparate phenomena. Electricity and magnetism turned out to be aspects of electromagnetism. Space and time turned out to be aspects of space-time. Perhaps consciousness and cosmos will turn out to be aspects of something deeper, something we haven't yet glimpsed. For now, we're left with wonder, and that's not a bad place to rest. Let that wonder settle as we continue, exploring how the question of cosmic origins relates to questions of meaning and purpose. Does the universe have a purpose? It's a question that science typically avoids, relegating it to philosophy or religion. Science describes how things work, not why they exist or what they're for. And yet, the question keeps arising, especially when we contemplate the origin of everything. If the universe came from nothing through a quantum fluctuation, does that make existence purposeless? An accident that happened because it could? Or is there something about the mathematical structure of reality that makes existence necessary, inevitable, even meaningful? Let's consider what we mean by purpose. In everyday life, purpose is connected to intention. A hammer has the purpose of driving nails because someone designed it for that purpose. A bird's wing has the purpose of flight because evolution shaped it for that function. In both cases, purpose emerges from a process, whether intelligent design or natural selection, that produces structure matched to a goal. But the universe as a whole can't have purpose in this sense unless there's something outside the universe, intending or selecting for certain outcomes. This is where religious and philosophical frameworks traditionally place God or some ultimate reality that grounds existence and gives it meaning. Science can't address whether such an external reality exists. It's not an empirical question. But science can ask whether there are patterns in the universe that suggest order, that suggest the cosmos is more than random chaos. And here, the answer is clearly yes. The laws of physics are astonishingly regular and mathematical. The same equations that describe falling apples describe orbiting planets. The same quantum mechanics that governs electrons governs quarks and photons. There's a deep unity to nature, a coherence that seems to demand explanation. Why should the universe be mathematical at all? Why should it follow laws that our minds can discover and understand? Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. Mathematics is a product of human thought, a set of abstract relationships we discover through logic. And yet, these abstract relationships turn out to describe the physical world with astonishing precision. Some physicists suggest that the universe is mathematical, not just described by mathematics, but actually made of mathematics. In this view, reality is the instantiation of mathematical structure, and the laws of physics are simply the logical relationships inherent in that structure. There's no distinction between the abstract and the concrete. They're the same thing viewed from different perspectives. This idea, sometimes called mathematical Platonism, solves certain problems but creates others. If reality is mathematics, why this particular mathematics? Why these laws and not others? The problem of existence just transforms into a problem of selection. What selects which mathematical structures get instantiated as physical universes? The multiverse offers one answer. All mathematical structures that are consistent and complex enough might be instantiated somewhere. The vast landscape of possibilities is fully realized across the multiverse. We find ourselves in a universe with these particular laws because we couldn't exist in most other mathematical structures. But this still leaves questions about meaning and value. Even if existence is explained, even if we understand why the universe is here and why it follows the laws it does, what does it all mean? Why should we care? What purpose does our own existence serve in this grand cosmic scheme here? Science reaches its limit. It can tell us what the universe is and how it works. It can tell us where we came from and, to some extent, where we're going. But it can't tell us what we should do with that knowledge or how we should live in light of it. Those are questions for philosophy, for ethics, for each of us as individuals trying to find meaning in our lives. And yet, there's something about the cosmic perspective that feels meaningful in itself. Knowing that we're made of stardust, that the atoms in our bodies were forged in the cores of dying stars billions of years ago. Knowing that the same carbon that makes up our cells has cycled through countless other organisms, been part of ancient forests and dinosaurs and bacteria. Knowing that we're participants in the universe's long evolution, from simplicity to complexity, from the nearly uniform gas of the early universe to galaxies and planets, and eventually life and mind. This narrative, this cosmic story gives a sense of belonging, of being part of something vastly larger than ourselves. It's not purpose in the teleological sense of moving toward a predetermined goal, but it's meaningful nonetheless, a framework for understanding our place in the grand scheme of things. Perhaps purpose isn't something the universe has, but something we create. We're meaning-making creatures. We find patterns, tell stories, build connections between things. We take the raw materials of existence and shape them into something significant. The universe provides the stage and the props, but we write the play. And maybe that's enough. Maybe the question, what came before the Big Bang, is ultimately part of this meaning-making activity. We ask because we're curious, because we want to understand, because the universe has given rise to beings capable of wondering about their own origins. The question itself is part of the purpose we create. There's a kind of beauty in that. The universe has evolved to the point where it can contemplate its own beginning. Atoms arranged in certain configurations, neurons firing in particular patterns, give rise to thoughts about the Big Bang and quantum fluctuations and eternal inflation. Matter thinking about matter. The cosmos understanding the cosmos. Let that thought rest gently as we turn our attention to what the latest observations and theories are telling us, and whether we're getting closer to an answer. We're living in a remarkable time for cosmology. Our observations have reached extraordinary precision. We've mapped the cosmic microwave background to exquisite detail. We've measured the expansion rate of the universe across billions of years of cosmic history. We've detected gravitational waves from colliding black holes, confirming Einstein's century-old prediction and opening a new window on the cosmos. And yet, the more we learn, the more we realise how much we don't know. Dark matter makes up about 27% of the universe's mass and energy, and we don't know what it is. Dark energy makes up about 68%, and we know even less about that. Ordinary matter, the stuff that makes up stars and planets and us, is only about 5% of the total. We're swimming in an ocean of mystery. The question of what came before the Big Bang sits at the intersection of these mysteries. It involves quantum mechanics, which we don't fully understand despite its empirical success. It involves gravity and general relativity, which we also don't fully understand, especially in extreme conditions. And it involves the unification of these two theories into quantum gravity, which we definitely don't have yet. But we're making progress. Experiments are getting more precise. The Large Hadron Collider has discovered the Higgs boson, confirming a key prediction of the standard model of particle physics. Future colliders might probe even higher energies, getting us closer to the conditions of the very early universe. Gravitational wave detectors are becoming more sensitive, and they might someday detect the primordial gravitational waves from inflation that would tell us about energies far beyond what we can reach in accelerators. Space-based telescopes are revealing the universe at wavelengths we couldn't observe from the ground. The James Webb Space Telescope is looking back to the first galaxies, seeing light from when the universe was only a few 100 million years old. Future telescopes might see even farther, perhaps detecting the first stars, the very first sources of light in the cosmos. All these observations constrain our theories. They tell us what's possible and what's not. Inflation has to produce the pattern of fluctuations we observe in the CMB. The amount of dark matter has to match what we infer from gravitational lensing and galaxy rotation. The expansion history of the universe has to match what we measure from distant supernovae and the CMB. These constraints are getting tighter. We're closing in on a detailed understanding of cosmic history from the first fraction of a second to the present day. The question is whether we can push even earlier, to the moment of the Big Bang itself, or to whatever came before. String theory and loop quantum gravity are both making progress, though in different directions. String theory has made connections with pure mathematics that have been fruitful for both fields. Loop quantum gravity has produced concrete models of the Big Bang bounce that can be compared with observations. Neither has been confirmed, but both are developing as rigorous scientific programs. There are other approaches too. Causal set theory, which treats space-time as a discrete set of events with causal relationships. Asymptotically safe gravity, which suggests that gravity becomes well-behaved at high energies without needing string theory or extra dimensions. Emergent gravity theories, which propose that space-time itself emerges from something more fundamental, perhaps quantum entanglement. Each of these approaches offers a different perspective on what might have come before the Big Bang. They're not all compatible with each other, and probably only one, if any, is correct. But the diversity of ideas shows that physicists are taking the question seriously, developing mathematical frameworks that could, in principle, be tested. What would constitute a satisfactory answer? What would it take for us to say, quote, _22 _? At minimum, we'd need a theory that makes testable predictions that are confirmed by observation. The theory would need to explain why the universe has the initial conditions we observe, why inflation happened, why the laws of physics are what they are. It would also need to be mathematically consistent, free from paradoxes and infinities that suggest something is wrong with the framework. And ideally it would connect to other areas of physics, explaining not just the Big Bang but also black holes, quantum mechanics, the nature of time, and perhaps even consciousness and the emergence of complexity. We're not there yet, but we're farther along than we were 50 years ago, when the Big Bang was barely accepted and inflation hadn't been conceived. In another 50 years, we might have answers that seem impossible now, or we might discover that some questions are genuinely beyond our reach, not for practical reasons, but for fundamental ones. Either way, the journey of trying to answer these questions is valuable in itself. It pushes the boundaries of human knowledge and understanding. It reveals the universe's workings in ever greater detail, and it connects us to something larger than our individual lives, to the grand project of understanding reality itself. As we move toward the final chapters of our 90 minutes, you've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. As we move toward the final chapters of our exploration, we'll consider what it means to live with uncertainty, to not know the ultimate answers, and whether there's a kind of wisdom in accepting the limits of knowledge while still pursuing truth as far as we can. There's a particular kind of comfort in not knowing everything. It leaves room for wonder, for discovery, for the unexpected. If we had all the answers, if every question had been resolved, what would there be left to explore? The mystery at the heart of existence. The question of what came before, or why there's something rather than nothing, might be a gift rather than a frustration. Science has answered so many questions that once seemed unanswerable. Why do objects fall? Why do diseases spread? What are stars made of? How old is the Earth? Each answer led to new questions, deeper mysteries, more refined understanding. The frontiers of knowledge keep expanding, and each new answer reveals new horizons of uncertainty. This is the nature of the scientific endeavour. It's not a march toward complete knowledge, but an endless process of refinement and expansion. We learn more about smaller and smaller details and larger scales. We develop better theories that explain more phenomena with greater precision. But we never reach a final theory, a complete description that answers every possible question. And that's okay. In fact, it might be essential. The cosmologist Sean Carroll has argued that science doesn't require ultimate explanations, only better and better theories that fit the data. We don't need to know why the laws of physics are what they are if we can accurately describe what those laws do. The why question might not even be well posed, might not have an answer in the way we expect. This perspective doesn't diminish the value of asking. Questioning is how we push boundaries, how we discover what we didn't know. The very act of formulating the question, quote 24, has led to inflation, to quantum cosmology, to ideas about the multiverse and quantum gravity. These ideas have deepened our understanding of the universe, even if they haven't yet given us a final answer. There's also something to be said for the experience of confronting mystery directly. It's humbling. It reminds us that we're not the centre of reality, that our intuitions and common sense are limited tools adapted to a narrow range of experiences. The universe doesn't owe us comprehensibility. The fact that we can understand as much as we do is remarkable. perhaps even miraculous in its own way. Many of the greatest scientists and thinkers have spoken about this sense of wonder in the face of the unknown. Einstein talked about the most beautiful emotion we can experience being the mystical, the encounter with something that transcends our ability to fully grasp. Not mysticism in the sense of supernatural belief, but a recognition of the profound depth of reality, the inexhaustible complexity that lies beneath every explanation. This doesn't mean giving up on understanding, it means holding two things in tension: the drive to know more and the acceptance that complete knowledge might not be possible. We push as far as we can, using reason and observation and mathematics, and when we reach the limits, we acknowledge them honestly rather than pretending to know more than we do. The question of what came before the Big Bang might be one of those limits, or it might not be. We won't know unless we keep asking. Keep developing theories, keep making observations. The answer, if it exists, will come from the patient work of many scientists over many years, building on each other's insights, following where the evidence leads. In the meantime, we can appreciate the question for what it is: a window into the deepest workings of reality, a challenge that calls forth our best thinking, and a reminder of how much remains to be discovered. The universe has given rise to beings capable of wondering about its origins. That alone is extraordinary. Whatever the answer to the wonder turns out to be, there's a kind of peace that comes from accepting this, from embracing the uncertainty without needing to resolve it immediately. The universe is vast and ancient and complex beyond measure. Our understanding is limited and provisional and always will be. And yet, we're part of this vast cosmos, made of its matter, shaped by its laws, participants in its unfolding story. That participation is enough. We don't need to know everything to live meaningful lives, to make discoveries, to experience beauty and connection and growth. The mystery doesn't diminish us. It invites us to keep exploring, to stay curious, to remain open to surprise. And so we continue our gentle drift through these ideas, ready now to explore what the philosophical implications might be, and whether there are ways of thinking about existence that complement the scientific perspective. Why is there something rather than nothing? This question, posed by the philosopher Leibniz 3 centuries ago, remains as puzzling today as it was then. It's the ultimate question, the one that all other questions about origin seem to rest on. Even if we explain how the universe emerged from a quantum fluctuation, or an inflating space, or a previous universe, we're left with the question, why does quantum mechanics exist? Why is there a framework for anything to happen at all? Some philosophers have argued that the question is meaningless. Nothing, they say, isn't a state that could have existed. The word nothing is just a linguistic construction, a way of talking about the absence of things, but not itself a thing that could be or not be. Existence is the default state, and asking why it exists is like asking why triangles have 3 sides. It's definitional, not explanatory. But this doesn't quite satisfy. When we imagine nothing, we're imagining not just the absence of objects, but the absence of space, time, laws, possibilities, complete metaphysical nothing. And it seems conceivable, at least in principle. We can think the thought. So why isn't that the case? Why is reality full rather than empty? One answer, proposed by philosophers and picked up by some physicists, is that nothing is unstable. If you had a state of complete nothingness, with no laws or structures or anything at all, that state might contain an inherent tendency to become something. Nothingness might be logically or metaphysically impossible, a contradiction that resolves itself by producing existence. This is the idea behind some versions of quantum creation of the universe. Nothing isn't stable because quantum mechanics doesn't allow perfect stillness or perfect emptiness. The uncertainty principle forbids it. So even from nothing, or from the closest thing to nothing that physics allows, a universe can emerge, must emerge, given enough time or timeless possibility. but this still assumes the existence of quantum mechanics, of some mathematical structure that governs possibilities. Where does that come from? You can keep pushing back, each answer generating a new question, until you either accept an infinite regress, a chain of causes extending back forever, or you accept something uncaused, something that exists without needing an external explanation. Philosophers call this the cosmological argument, and it's been used as an argument for God. If everything that exists has a cause, and the chain of causes can't be infinite, then there must be a first cause, an uncaused cause, and that cause is God. The argument has a long history and many sophisticated versions, but it also has well-known problems. The main problem is that if we allow for an uncaused cause, something that exists without needing explanation, why not just let the universe itself be that thing? Why add an extra step? If God can exist without needing a cause, why can't the universe? This is called special pleading, applying a principle to everything except the thing you want to exempt. Some theologians respond by saying God is metaphysically necessary, existing in all possible worlds, whereas the universe is contingent, existing in some possible worlds, but not others. But this distinction itself needs justification. What makes God necessary and the universe contingent? Without a clear answer. The argument becomes circular. There's another approach, one that embraces the mystery rather than trying to resolve it. This is the existentialist perspective, associated with philosophers like Jean-Paul Sartre and Albert Camus. They argued that existence precedes essence, that there's no predetermined purpose or explanation for why things are. We're thrown into existence without asking for it, and we must create meaning for ourselves in a universe that offers no inherent meaning. This might sound bleak, but it can also be liberating. If there's no cosmic purpose, then we're free to choose our own. If the universe doesn't care what we do, then we're responsible for making our lives matter, for creating value through our choices and actions. The absence of external meaning is an opportunity, not a tragedy. But even this existentialist freedom assumes existence as a given. The question remains, why is there this existing universe in which we can be free? Why is there something for us to be thrown into? Perhaps the answer is that there isn't an answer, not in the sense of a further explanation. Existence might be a brute fact, something that's true without being derivable from anything more fundamental. We reach bedrock, the point beyond which explanation can't go, and we simply have to accept that this is how things are. This isn't satisfying to our desire for ultimate explanations. We want to know the reason for everything. But maybe some things just are, without reasons. The mistake is thinking that everything must have an explanation in terms of something else. Some facts are fundamental, and existence might be one of them. Or perhaps, as some modern philosophers have suggested, all possible mathematical structures exist, and we're in one of them simply by virtue of being able to ask the question. In this view, known as mathematical Platonism, or the mathematical universe hypothesis, existence is cheap. Everything that can exist does exist in some abstract sense, and the question is not why there's something rather than nothing, but why we find ourselves in this particular something. These ideas connect back to the multiverse and the anthropic principle we discussed earlier, but they add a philosophical dimension, asking about the nature of existence itself, about what it means for something to be real rather than merely possible. As we think about these deep questions, let's consider how they relate to our experience of being here, of living in this particular universe at this particular moment in its history. There's something profound about the fact that things could have been otherwise. The universe could have had different laws, different constants, different initial conditions. We could have not existed. Earth could have not formed. Life could have never arisen. Each moment, each existence is contingent, dependent on countless prior events that didn't have to happen but did. This contingency is sometimes seen as making life meaningless. If we're here by accident, the product of random processes and unlikely chances, what significance can our existence have? But there's another way to look at it. The very fact that things could have been different, that our existence is improbable and contingent, makes it more precious, not less. Think about the chain of events that had to occur for you to be here right now. Your parents had to meet. Their parents had to meet. Going back through generations, every single one of your ancestors had to survive long enough to reproduce. A single broken link in that chain, and you wouldn't exist. Go back further, and the contingency deepens. Life had to arise on Earth. Earth had to form in the Sun's habitable zone. The Sun had to form from a cloud of gas enriched with heavy elements from earlier generations of stars. Trace it all the way back, and your existence depends on the initial conditions of the Big Bang, the quantum fluctuations that grew into galaxies, the precise values of the constants of nature that allow for stars and planets and chemistry and life. If any of these had been slightly different, you wouldn't be here. The universe would exist, but not in a form that could support human life, or perhaps any life at all. This is the fine-tuning problem, and it's one of the most puzzling observations in cosmology. The constants of nature seem to be set with extraordinary precision to allow for complexity. Change the strength of the electromagnetic force by a small amount, and atoms can't form. Change the strength of the strong nuclear force, and stars can't fuse hydrogen into heavier elements. Change the amount of dark energy, and either the universe collapses almost immediately or expands so fast that galaxies never form. There are dozens of these apparent fine-tunings, and collectively they create what's sometimes called the Goldilocks enigma. The universe is just right for life. Not too hot, not too cold, not too much gravity, not too little. Just right. Why? The multiverse offers one answer. If there are countless universes with different constants, then it's not surprising that at least one has the right values for life. We observe this one because we couldn't observe any other. The fine-tuning isn't mysterious, it's just selection bias. We're in the subset of the multiverse that permits observers. But even if we accept the multiverse explanation, there's still something remarkable about being one of the observers. Out of all the possible universes, we happen to be in one where the constants allow for stars and planets and chemistry and biology, and eventually minds capable of understanding the cosmos. That's extraordinarily unlikely, even given a multiverse, and it suggests that being here, being aware, being able to ask these questions, is genuinely special. There's a theological perspective worth considering, even if you don't share its assumptions. The idea is that the universe is fine-tuned because it was designed to be. God set the constants to allow for life because God wanted creatures capable of relationship, capable of love and knowledge and moral choice. The fine-tuning. In this view is evidence of purpose, of a cosmos that was meant to produce us. Science can't confirm or refute this. Design is not a hypothesis you can test with observations. You can't compare universes with and without designers to see which is which. But as a philosophical framework, it offers a way of understanding why things are the way they are. The universe has the properties it does because those properties serve a purpose, and that purpose involves the existence of beings like us. Whether you find that persuasive depends on your broader philosophical commitments. But what's clear is that the contingency of existence, the fact that things could have been otherwise, raises questions that science alone can't fully answer. We can describe the universe in exquisite detail. We can explain how things work. But the question of why things are set up to work this way, why the universe is hospitable to life, touches on philosophy and theology and meaning in ways that go beyond empirical observation, and perhaps that's appropriate. The question of what came before the Big Bang is ultimately connected to questions about why anything exists at all, and those are questions that have occupied human thought for as long as we've been capable of abstract reasoning. They're not new questions posed by modern cosmology. They're ancient questions given new urgency and precision by our growing understanding of the cosmos. The gift of contingency is that it makes existence wondrous. If everything were necessary, if things couldn't be any other way, there would be no mystery, no room for gratitude or awe. But because things are contingent, because we exist by a combination of chance and necessity that we're only beginning to understand, our existence feels like a gift, unearned and precious. And whether that gift has a giver, whether there's a purpose behind it all, or just the cold workings of physics and chance, we're here to receive it and to do something with it. To create meaning and beauty and understanding in this brief window of time we have. Let that thought rest as we explore what time itself means, and whether the past and future are as real as the present moment. In our everyday experience, time flows. The past is gone, fixed and unchangeable. The future hasn't happened yet and is open, full of possibilities. The present is this fleeting moment where we exist, where we make choices and experience reality. This seems so obvious that it's hard to imagine time being any other way. But modern physics suggests that this view of time might be an illusion, a feature of our consciousness rather than a feature of the universe. In Einstein's relativity, time doesn't flow. All moments, past, present and future, exist equally in a four-dimensional space-time. The passage of time is no more real than the passage of space when you move from one location to another. This is called the block universe view. And it has profound implications for our question about what came before the Big Bang. If all of time exists as a single four-dimensional structure, then quote 26 doesn't mean what we ordinarily think it means. The Big Bang isn't the first moment in a sequence of moments. It's one end of a four-dimensional object, the space-time manifold, which extends from the Big Bang to whatever future awaits the universe. In this view, you exist not just at this moment, but at every moment of your life simultaneously. Your birth and your death are equally real, equally part of the space-time structure. The only thing that changes is which moment you're experiencing, which slice of space-time your consciousness is currently aware of. But from the perspective of the universe as a whole, all of it exists at once. This is challenging to wrap your mind around because it contradicts our deep intuition that the present is special, that now is fundamentally different from past and future. But the physics supports it. In relativity, there's no universal now. Events that are simultaneous for one observer are not simultaneous for another observer moving at a different velocity. The concept of now is observer-dependent, not built into the structure of space-time. If the block universe is correct, then asking what came before the Big Bang is like asking what's before the first page of a book. The book exists as a complete object. You can read it from front to back, but the first page isn't caused by anything before it. It's simply where the book begins. Similarly, the Big Bang might be where space-time begins, not because something caused it to begin, but because that's the boundary of the four-dimensional structure. But not all physicists accept the block universe. Some argue that time is more fundamental, that the passage of time is real and not just an illusion of consciousness. They point to the arrow of time, the fact that entropy increases, that eggs break but don't unbreak, that there's a clear distinction between past and future at the macroscopic level. The many worlds interpretation of quantum mechanics offers a way to reconcile these. In many worlds, all possible outcomes occur, but in different branches of the universe. The block universe would then be vastly more complex than a single timeline. It would be a branching structure, a tree of possible histories all equally real. Your future isn't a single path, but an infinite array of paths, and which one you experience depends on which branch of the quantum wave function you're on. This is speculative, and there's no consensus on which view of time is correct. But what's important for our question is that the nature of time itself is part of the mystery. We can't fully understand what came before the Big Bang without understanding what time is, whether it's fundamental or emergent, whether the future is real or open, whether the past still exists or is truly gone. And as we think about these questions, we might find that our ordinary experience of time, as limited as it is, still gives us genuine insight into the nature of reality, even if that reality is stranger and more complex than we naturally assume. We're accustomed to thinking in terms of cause and effect. Every event has a cause. If something happens, something else made it happen. This is such a fundamental part of how we understand the world that it's hard to imagine reality working any other way. And yet quantum mechanics and cosmology both suggest that causality might not be as fundamental as we think. In quantum mechanics, events can happen without causes, or at least without deterministic causes. When a radioactive atom decays, there's no prior state that determines when the decay will occur. It's genuinely random. You can calculate the probability of decay in a given time interval, but you can't predict the exact moment. The decay happens, in some sense, without a cause. This troubled Einstein deeply. He famously said that God does not play dice with the universe, expressing his discomfort with the randomness at the heart of quantum theory. But experiments have confirmed that quantum randomness is real. Particles like electrons don't have definite properties until they're measured. And the outcome of the measurement is fundamentally unpredictable. If quantum mechanics allows for uncaused events at the microscopic level, might it allow for an uncaused event at the cosmic level? Could the Big Bang itself be an uncaused event, a quantum fluctuation that happened without anything making it happen? This is the essence of quantum creation models like Vilenkin's. The universe begins spontaneously, not because something caused it to begin, but because the laws of quantum mechanics permit it to begin. But this only pushes the question back. If quantum mechanics permits uncaused events, where does quantum mechanics come from? Why are the laws of physics set up this way? You might say the laws themselves don't need a cause, they're just the way reality works. But that's a significant philosophical move, accepting that some things are brute facts without further explanation. There's another way to think about causality that might help. Instead of thinking of causes as earlier events that produce later events, we can think of them as explanatory relationships. The cause explains the effect, gives the reason why the effect occurs. In this view, asking for the cause of the Big Bang is asking for an explanation, a reason why the universe exists. And there might be explanations that aren't temporal. A mathematical truth doesn't have a cause in time. The fact that 2 + 2 = 4 isn't caused by an earlier event. It's a logical necessity, true in all possible worlds. If the existence of the universe is somehow logically necessary, if it flows from the nature of mathematics or logic itself, then it would have an explanation without having a temporal cause. This is the approach taken by some philosophers and physicists who argue that existence is necessary. The laws of physics, they suggest, are not contingent facts that could have been otherwise, but necessary truths that must be as they are. The universe exists because non-existence is logically impossible, or because the mathematical structure that describes reality must be instantiated. The multiverse enters again here. If all possible structures exist somewhere in the multiverse, then our universe's particular structure isn't special. It's one possibility among many, and we observe it because we're in it, because our existence requires this particular kind of structure. The question of why this structure shifts from why does it exist, to why are we in this part of the structure rather than another, and that question might have an anthropic answer. We're here because we can only be in a universe with laws that permit complexity, chemistry, biology, consciousness. Most possible universes, most possible structures, don't have those properties. We observe the subset that does. This still leaves a kind of mystery, but it's a different kind. It's not the mystery of why there's something rather than nothing, but the mystery of why the something that exists includes beings capable of asking the question. And perhaps that's the right mystery, the one that acknowledges both our cosmic insignificance and our cosmic significance. We're insignificant in that we're a tiny part of a vast universe, possibly one universe among infinitely many. But we're significant in that we're the part that can understand, that can trace the chain of causality back to the Big Bang and ask what came before, that can contemplate the nature of existence itself. As we move toward the final chapters, we'll explore what this all means for how we live, how we think about our place in the cosmos, and what wisdom might emerge from sitting with these impossible questions. There's a particular kind of maturity that comes from accepting uncertainty, from living with questions that might not have answers, at least not in your lifetime. It's the maturity of recognizing the limits of knowledge while still pursuing truth as far as you can. And it's a maturity that the question of what came before the Big Bang invites us toward. Our ancestors had certainty, or at least they thought they did. Creation myths explained where everything came from. Gods formed the world from primordial chaos, or spoke it into being from nothing. These stories provided answers, frameworks for understanding existence. They weren't scientific in the modern sense, but they served a purpose, giving meaning and structure to human life. With the rise of science, we traded some of that certainty for something else. Provisional knowledge that's constantly being refined, questions that generate more questions, mystery that deepens rather than resolves. And that trade-off, difficult as it sometimes is, has given us an extraordinary gift, genuine understanding of how nature works, the ability to predict and control and manipulate the physical world in ways our ancestors couldn't have imagined. But it's also left us with a kind of existential uncertainty. We know so much more than any previous generation, and yet we're also more aware of how much we don't know. The universe is vastly larger, older, and more complex than anyone imagined a few centuries ago. Our place in it is smaller, more contingent, more dependent on chance and on physical processes that don't care about our existence. This can be unsettling. If the universe is the result of a quantum fluctuation, if our existence is an accident in an uncaring cosmos, what grounds our lives? What makes anything matter? These are the questions that keep people awake at night, that drive some toward religion and others toward nihilism. But there's a third option, one that embraces uncertainty without succumbing to despair. It's the recognition that meaning doesn't have to come from outside. We can create it ourselves. The universe might not care about us, but we care about each other. We care about beauty and truth and justice. We care about understanding the cosmos, even if the cosmos doesn't understand us back. None of these frameworks has a monopoly on truth or meaning. They're different ways of engaging with the mystery of existence, different lenses through which to view the same underlying reality. And perhaps that diversity is itself valuable, a reflection of the richness and complexity of human experience. The wisdom of uncertainty is knowing that you don't have to have all the answers to live a good life, to contribute to human knowledge, to experience wonder and joy and connection. It's knowing that the journey matters as much as the destination, and that some questions are worth asking even if they can't be fully answered. It's also recognizing that our understanding is always provisional, always subject to revision in light of new evidence. The theories we hold today might be replaced by better theories tomorrow. The questions we can't answer now might yield to future generations with better tools and new insights. Or they might not, and that's okay too. What matters is the pursuit itself, the commitment to following where evidence and reason lead, to being honest about what we know and what we don't, to remaining open to surprise and discovery. This is the scientific spirit at its best, and it's a spirit that can guide us not just in cosmology but in all areas of life. As we approach the final chapters of our exploration, we'll turn our attention to what it means to live in a universe with this kind of origin, and what peace we might find in contemplating our place within the vast cosmic story. Consider the span of human existence against the age of the universe. Anatomically modern humans have been around for about 300,000 years. Civilization, with cities and writing and complex social structures, is only about 10,000 years old. Science, as we know it, is a few centuries old, and the universe is 13.8 billion years old. If you compress the entire history of the universe into a single year, with the Big Bang happening at midnight on January 1st, humans wouldn't appear until December 31st at around 11:30 at night. All of recorded history, every empire and war and discovery and work of art, would fit into the last few minutes before midnight. Our individual lives are fractions of a second in this cosmic year. This perspective can be humbling to the point of feeling insignificant. were so brief, so small, so recent. The universe existed for billions of years before us, and will likely exist for trillions of years after. We're a tiny blip in an incomprehensible vastness. And yet, there's another way to look at it, one that restores a sense of significance without denying the scale. We're the part of the universe that's become conscious, that can reflect on its own existence. For billions of years, matter arranged itself in increasingly complex patterns. Atoms formed from the primordial plasma, stars condensed from clouds of gas, heavy elements were forged in stellar cores and scattered by supernova, planets coalesced from the debris, and eventually, on at least one planet, life emerged. Life is matter, organised in a special way, capable of maintaining itself, reproducing, evolving, and eventually, through billions of years of evolution, life gave rise to nervous systems, brains, minds. Consciousness emerged. The universe became aware of itself. Atoms arranged themselves into configurations capable of thinking about atoms. And that awareness, brief as it is precious. For a few decades, you get to experience existence. To think and feel and wonder, to ask questions like quote 30 and to search for answers, that's a gift, one that most of the matter in the universe never receives. Let that awareness settle gently as we continue, exploring what it means to be part of this vast unfolding story. There's a strange beauty in the mathematics that describes the universe. Einstein's field equations, which govern the curvature of space-time, can be written in a few lines. The Schrödinger equation, which governs quantum mechanics, is similarly compact. These equations, simple enough to fit on a t-shirt, contain within them the behaviour of everything from falling apples to colliding galaxies to the quantum fluctuations that gave rise to the large-scale structure of the cosmos. Why should the universe be mathematical? Why should it follow rules that can be expressed in equations, that can be manipulated with logic and calculation? This is a deep mystery, one that physicists and philosophers have pondered without reaching a consensus. But the fact remains, mathematics works. It describes reality with astonishing accuracy, and the mathematics is beautiful in a way that's hard to explain to someone who hasn't experienced it. Equations have elegant symmetry, simplicity. The best physical theories are not just accurate but aesthetically pleasing. They have a kind of inevitability, a sense that this is how things had to be. Einstein's general relativity, for instance, is based on the principle that the laws of physics should look the same to all observers, regardless of their motion. From this simple principle, combined with the mathematics of differential geometry, the entire theory flows. Space-time curvature, black holes, the expanding universe, all are consequences of demanding that symmetry. This aesthetic dimension of physics is more than decoration. Physicists often use beauty as a guide when developing new theories. If an equation is ugly, full of arbitrary terms and special cases, it's probably wrong. If it's elegant and simple, it's more likely to be true. This heuristic has led to many discoveries. Paul Dirac, one of the founders of quantum mechanics, famously said that it's more important for an equation to be beautiful than for it to match experiment, because if it's beautiful, it will eventually be found to be correct. That's a bold claim, and it doesn't always work. But there's something deep here about the relationship between truth and beauty, between the structure of reality and the sense of rightness that we experience when we grasp that structure. It's as if the universe is designed to be comprehensible, to reveal its secrets to minds patient and careful enough to look. This brings us back to our question about what came before the Big Bang. The equations that describe the Big Bang are beautiful in their own right. The Friedmann equations, which govern the expansion of the universe, follow from Einstein's field equations when you assume that the universe is homogeneous and isotropic on large scales. These equations tell us how the universe expands or contracts, depending on its matter and energy content. They predicted the Big Bang before it was observed, and they've been confirmed by countless observations since. but these equations also tell us that they break down at the Big Bang itself. When you run them backward in time, the density and temperature increase without limit. You reach a singularity, a point where the mathematics stops working. This suggests that something is missing, that the equations need to be extended or replaced by a more complete theory. Quantum gravity, when we finally have it, will presumably be beautiful in the same way that general relativity and quantum mechanics are beautiful. It will unify two seemingly incompatible theories into a single framework that's elegant and simple and has a sense of inevitability. And it will tell us what happens at the Big Bang, what replaces the singularity, what came before in whatever sense _quote_31_ makes in that context. We don't have that theory yet, but we have hints. String theory suggests that the fundamental objects are not points but extended strings, and this extension smooths out the singularities that plague point-particle theories. Loop quantum gravity suggests that space-time itself is quantized, made of discrete chunks, and this discreteness prevents densities from becoming infinite. Both approaches have their own mathematical beauty, their own elegance and symmetry. And both suggest that the Big Bang is not the end of the story but a transition, a phase change, a boundary that can be understood and perhaps even crossed by the right mathematics. This is hopeful in a way. It suggests that the universe is comprehensible all the way down or all the way back, that there are no final barriers to understanding, only barriers that await better theories. The beauty of the mathematics is more than aesthetic. It's a clue, a hint that we're on the right track. When the equations work, when they predict things we later observe, when they unify disparate phenomena under a single framework, we gain confidence that we're describing reality as it actually is, not just making models that happen to fit the data. This is the miracle of mathematics, its unreasonable effectiveness. We start with abstract patterns, with logical relationships between symbols, and somehow these patterns correspond to the physical world. An equation written on paper or in a computer describes the motion of planets, the decay of atoms, the expansion of space. It's as if the universe is made of mathematics, or as if mathematics and physics are two sides of the same coin. And if that's true, then perhaps the question of what came before the Big Bang is ultimately a mathematical question. Perhaps the answer lies not in observing what happened, but in understanding what's mathematically possible, what structures can exist, what equations can describe. Perhaps existence itself is a mathematical structure, and the Big Bang is a feature of that structure that we're learning to understand. This is speculative, but it's grounded in the deep connection between mathematics and physics that has proven so fruitful for centuries. And it suggests a kind of optimism, that the questions we're asking, even the seemingly impossible ones, might eventually yield to patient thought and careful calculation. Let's carry this sense of wonder at the mathematical structure of reality forward as we explore what it means to exist within this structure. There comes a point in every deep investigation where you reach the limits of what can be known with current tools and methods. In cosmology, that limit is approaching fast. We've traced the history of the universe back to fractions of a second after the Big Bang. We've measured the composition of the cosmos with precision. We've mapped the distribution of galaxies across billions of light years. And yet, the ultimate questions, the ones about origins and endings, about why rather than how, remain just beyond our grasp. This is frustrating if you expect science to provide complete answers to every question. But it's also appropriate. The universe is vast and complex, and we're finite beings with limited perspectives. We see a small slice of space and time, and from that slice we try to infer the whole. That we can do this at all, that we can look at light from billions of years ago and understand what it's telling us, is remarkable, but there will always be limits. Some might be practical. We can't observe beyond the cosmic horizon. We can't probe energies higher than what our accelerators can reach. We can't test theories that make predictions only on scales or timescales we can't access. Others might be fundamental. There might be questions that can't be answered because they're not well defined, or because the answer depends on a framework we haven't yet developed, or because reality is genuinely indeterminate at some level. The question of what came before the Big Bang might be one of these fundamentally limited questions, or it might not be. We won't know until we know, and in the meantime, what do we do? We could demand certainty and be frustrated when it's not forthcoming. We could give up and say the question is unanswerable, or we could accept the mystery and continue working at its edges, refining our theories, making new observations, following where the evidence leads even if we don't yet see the destination. This third option, acceptance without resignation, is what I think characterises the best scientific and philosophical thinking. It's the ability to live with questions that don't have answers yet, to work toward understanding without needing to have already arrived. It's intellectual humility combined with ambition, the recognition that we don't know everything paired with the drive to know more. And there's a kind of peace in this acceptance. When you stop demanding that the universe make complete sense to you right now, when you accept that some things are genuinely mysterious and might remain so for a long time or forever, a weight lifts. You can engage with the mystery out of curiosity and wonder rather than frustration and need. This doesn't mean giving up on answers. It means holding them lightly, being willing to revise your understanding when new evidence comes in, staying open to the possibility that the truth is stranger than you imagined. Some of the greatest discoveries in science came from people who were willing to accept that their intuitions might be wrong, that the universe might work in ways that seem impossible or absurd at first. Quantum mechanics is a perfect example. The idea that particles can be in two places at once, that observation affects what's being observed, that there's fundamental randomness in nature, all these seemed crazy when they were first proposed. They contradicted everything we thought we knew about how reality works. And yet, experiment after experiment confirmed them. The universe is genuinely weird, weirder than common sense would ever suggest. The same might be true about what came before the Big Bang. The answer, when and if we find it, might be something we can't currently imagine, something that requires us to rethink basic concepts like time and causality and existence. It might involve dimensions we can't visualize or mathematics we haven't yet developed, and that's okay. The universe doesn't owe us an easily comprehensible answer, but even if the answer is forever beyond our reach, the process of asking matters. The question drives us to think more deeply about time and space and quantum mechanics. It connects us to the long history of human inquiry into the nature of reality. It reminds us of our place in the cosmos, small but significant, temporary but aware. And it invites a particular kind of contemplation, one that's comfortable with not knowing, that finds value in the question itself rather than only in the answer. This is a contemplative stance that many spiritual traditions cultivate, the ability to sit with mystery, to let it be what it is without needing to resolve it. Science and spirituality don't have to be in conflict here. They can both be approaches to the same deep questions, using different methods and languages, but ultimately concerned with understanding the nature of existence. Science uses observation and mathematics. Spirituality uses meditation and metaphor. Both can arrive at genuine insights, and both can complement each other if we let them. The mystery of what came before the Big Bang is big enough to hold multiple approaches. We can study it scientifically, developing theories and making observations. We can contemplate it philosophically, thinking about causality and time and existence. We can experience it spiritually, feeling awe and wonder at the vastness of the cosmos and the improbability of our existence within it. And all of these are valuable. All of them enrich human life and expand human understanding. The question doesn't have to have a single answer or a single approach. It can be a meeting ground for different ways of knowing, different frameworks for making sense of reality. As we approach the final chapter, let's think about what this all means for how we live, how we relate to each other, and to the universe that gave us birth. After all this exploration, after journeying through quantum mechanics and general relativity, through multiverse theories and cyclic cosmologies, through philosophy and physics and the nature of time itself, where do we find ourselves? We're here now, in this particular moment of cosmic history, aware of our origins in a way that no previous generation has been, and still uncertain about the ultimate beginning. And perhaps that's exactly where we should be. Not at the end of understanding, but somewhere in the middle, knowing enough to ask good questions, but humble enough to admit we don't have all the answers. This is a good place for humans to be, a place of both knowledge and wonder, of confidence in what we've learned and openness to what we might still discover. The question of what came before the Big Bang has led us through the entire history of the universe and beyond, into speculations about quantum gravity and multiverse cosmology and the nature of existence itself. And in doing so, it's revealed something important about the human mind and spirit. We're creatures who need to know where we came from. We can't be content with just experiencing existence. We need to understand it, to place ourselves within a larger story, to know our origins. This need is ancient. Every culture has had creation myths, stories about how the world began and how humans came to be. These myths served important functions. They explained the unexplained, gave meaning to existence, connected people to their ancestors and their gods, provided frameworks for understanding suffering and death and the cycles of nature. Modern cosmology is, in some sense, our creation myth. It's based on observation and mathematics rather than revelation and tradition, but it serves some of the same functions. It tells us where we came from the Big Bang, from cooling plasma and coalescing gas, from stars that lived and died before the sun was born. It explains the unexplained, why the sky is dark at night, why galaxies are moving apart, why the cosmic microwave background fills the universe. And it gives us a sense of place, of belonging to something vast and ancient. We're not separate from the cosmos, observing it from the outside. We're part of it, participants in its long unfolding, expressions of its capacity for complexity and awareness. This is our home, the only home we have, and understanding it is a way of understanding ourselves. But home is not just a place, it's also a feeling, a sense of belonging and rightness. And I think there's a way to feel at home in the cosmos, even while acknowledging its vastness and our smallness within it. It's the feeling of connection, of being related to everything else, of sharing a common origin in the Big Bang and a common fate in the far future when the stars burn out and the universe grows cold and dark. This connection is literal. The atoms in your body were made in stars. The energy that powers your cells came ultimately from the sun, which is powered by nuclear fusion, the same process that occurred in the first minutes after the Big Bang. The space you occupy is part of the same space-time fabric that's been expanding since the beginning. You're cosmically connected, woven into the structure of reality in ways both obvious and subtle. And this connection extends to everyone else. We're all made of stardust. We all share the same distant origin. We all exist because the universe happened to have the right properties for stars and planets and life. This shared cosmic heritage is more fundamental than any of the differences that divide us. We're family, cosmically speaking, children of the same universe, temporary expressions of the same underlying patterns. Remembering this can change how we relate to each other and to the world. If we're all made of the same stuff, if we're all part of the same cosmic story, then harming others is harming ourselves, harming the universe's capacity for experience and awareness. Taking care of each other and of the planet becomes not just a moral imperative but a cosmic one, a way of honouring the extraordinary process that led to our existence. And it can change how we think about meaning and purpose. If there's no cosmic plan, no external purpose imposed from outside, then we're free to create our own. We can decide what matters, what's worth working toward, how we want to live. This freedom is both exhilarating and terrifying, but it's the freedom that comes from understanding our true place in the cosmos. We're not at the centre. We're not the reason the universe exists. But we're also not insignificant. We're the way the universe becomes aware of itself, the way it reflects on its own existence. And that's a kind of significance that doesn't depend on being central or being the goal of creation. It's the significance of participation, of being part of the story rather than standing outside it. So what came before the Big Bang? We've explored many possibilities. Quantum fluctuations from nothing, eternal inflation creating bubble universes, cyclic cosmologies with endless bounces, multiverse scenarios where all possibilities are realized, even the idea that before might not be meaningful because time itself began at the Big Bang. We don't know which, if any, of these is correct. We might never know with certainty. But we've learned that the question is approachable, that it's not purely metaphysical, but has scientific dimensions that we can study and test. We've learned that the universe is far stranger and more wonderful than common sense suggests. And we've learned that asking impossible questions can lead to genuine understanding, even if the answers remain elusive. Most importantly, we've learned something about ourselves and our place in the vastness. We're small, yes, but not insignificant. We're temporary, yes, but connected to eternity through the laws of physics and the matter we're made of. We're part of a process that began 13.8 billion years ago and that will continue long after we're gone. And for this brief moment, we have the extraordinary privilege of being aware, of asking questions, of seeking truth. That's the real answer to what came before the Big Bang, or at least the answer that matters most for how we live. We came from the cosmos. We're made of it. Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. We came from the cosmos. We're made of it. We're expressions of its complexity, and one day we'll return to it, our atoms dispersing to form new structures, new possibilities. In the meantime, we have this moment, this awareness, this opportunity to wonder and understand and connect. And perhaps that's enough. Perhaps the journey of asking and exploring and discovering is itself the meaning, the purpose, the point. We exist because the universe allows us to exist. We're aware because the universe has become aware through us. And we ask what came before because the universe is asking through us, exploring its own origins through the minds it has created. This is coming home to the cosmos, recognizing that we belong here, that we're part of the story, that our questions and our seeking are themselves cosmic events, part of the long evolution from simplicity to complexity, from unconsciousness to awareness. We're home, and we've been home all along. We just needed to understand the journey to recognize where we've always been. Thank you for staying with me through this entire journey, through these 2.5 hours of slow drift, through one of the biggest questions we can ask. We've travelled together from quantum fluctuations to eternal inflation, from the mathematics of space-time to the philosophy of existence, from the very beginning of everything to the question of what might have come before beginning itself. That's no small journey, and I'm grateful you took it with me. From the cosmic microwave background carrying echoes of the Big Bang's first light to the speculative frontiers of quantum gravity and multiverse theory, from ancient philosophical questions about being and nothingness to cutting-edge observations from telescopes and gravitational wave detectors, we've explored what humans currently know and suspect about cosmic origins. The answer, as honestly as I can give it, is that we don't fully know what came before the Big Bang, or even whether, quote, 33 is meaningful in that context. But we have frameworks for thinking about it, theories that might someday be tested, and an understanding that's deeper than any previous generations. Perhaps the answer is that the universe emerged from a quantum fluctuation. Reality borrowing energy from nothing and not yet paying it back. Perhaps it's that our Big Bang was one bubble in an eternally inflating space that has always existed and always will. Perhaps it's that time itself emerged at the Big Bang, making, quote, 34 as meaningless as asking what's north of the North Pole. Or perhaps it's something we haven't yet imagined, something that will require new mathematics and new ways of thinking about existence itself. What we've learned suggests that the question is approachable, that science can push back the boundary of the unknowable, that what seemed impossible to investigate might yield to patient thought and careful observation. And even if some version of the mystery remains forever, the asking has value, the exploration has meaning, the journey toward understanding is worth taking. If you enjoyed this slow drift through the cosmos and its deepest questions, really helps others find these peaceful explorations. If you'd like to share your thoughts about what came before, or about your own relationship with these big questions, the comments are always open. I read them all, and there's something wonderful about this community of people who seek understanding as a way to wind down, who find peace in contemplating the vast rather than anxiety. And to those already subscribed, thank you for being here, for making this possible, for being fellow travellers in this journey of cosmic curiosity. Wherever you are in the world right now, I hope you're comfortable. I hope your breathing has slowed, that your thoughts have quieted, that your body feels heavy and warm and ready for rest. I hope the day's concerns have drifted away, at least for a while, replaced by wonder at the extraordinary fact of existence itself. Look up at the night sky, if you can, or imagine it if you can't. All those stars, hundreds of billions in our galaxy alone, each one a sun with potentially its own planets, its own story. And beyond them, hundreds of billions of other galaxies, stretching out to the edge of the observable universe and perhaps infinitely beyond. All of it emerged from the Big Bang, from that first moment of unimaginable density and temperature. All of it shares a common origin in that cosmic beginning, or in whatever came before. And you're part of it, connected to it all through the atoms in your body, and through the laws of physics that govern both you and the most distant galaxy. When you breathe in, you're breathing in atoms that were once in stars, that were once in ancient seas, that cycled through countless other organisms before reaching you. When you look at the stars, you're seeing light that travelled for years or centuries or millennia to reach your eyes. Photons that left their source long ago carrying information about distant suns. You exist in this particular moment, in this particular universe, able to think these thoughts and ask these questions because of a chain of events stretching back 13.8 billion years, from the Big Bang to the formation of atoms, from the first stars to the creation of heavy elements, from the birth of the sun to the formation of Earth, from the first stirrings of life to the long evolution that led eventually to you. Every link in that chain had to hold for you to be here now. And here you are, aware of it all, contemplating your own origins and the origins of everything. That's extraordinary. That's precious. In the end, what came before the Big Bang might matter less than what came after. This universe, this galaxy, this planet, this moment, this awareness. We exist because the universe allows it, because the laws and constants happen to permit complexity and life and mind. That might be accident or necessity or design, we don't know, but we know it's real and we know we're part of it. Sleep well. Dream of quantum foam and bubble universes, of space-time curvature and cosmic inflation, of stars being born and galaxies dancing through the void. Dream of the first moment, whatever that was, and of all the moments that followed, leading step by step to this one. Dream of questions that might never have complete answers, but that are worth asking nonetheless. Dream of the cosmos understanding itself through you. And when you wake tomorrow, remember, you're made of the universe, and the universe is made of you. You belong here, You're part of the greatest story there is, the story of existence itself, unfolding moment by moment from that mysterious beginning to whatever future awaits. Good night.